Hello, good afternoon, guys. Thank you for being here. I'm Jeonghoon Shin from South Korea. Today I'm talking about the journey of browser hacking with Angular. But before we start, let me tell you one of my concerns. That is, I can't speak English very well, and so 어디였지? Sorry. If I can make eye contact with you guys, because I'm reading my script. It is not because I don't like you. Please be kind to me. So let me introduce myself. So I'm working on theory for 5 years. Also, my position is security researcher, and I usually focusing on browser and kernel research. Also, I'm mentor of the best program called BoB. BoB is a cybersecurity education program in South Korea. It has been operating for 11 years and has educating about 1,400 students. In competitions like DEFCON, you can see the many teams that BoB students belong to. Also, I have traveled to some countries around the world for conference speaking. Those are that I talked about before the COVID issue. That COVID issue haven't been resolved yet, but this time, Singapore will be added to this list. So, before we start, I share what I got from Angular journey. This bug list is what I report to Chrome. I had a lot of good experience with the Chrome bug bounty. If you think your bug is not exploitable, to report it to a Chromium bug bounty program. And this list is the bugs I reported to GDI and Apple. The first few are reported through GDI, and one was reported through Apple. Those are the reward I got from Angular for about 1 year. So now let's get started. Begin with today's agenda. This is agenda for today. We figure out Angular project and WebGL components, and look at the bugs I found in Angular project and root cause analysis for them. Finally, we are going to look at how to exploit the Safari browser within exploitable vulnerability. So, let's start with the definition of an Angular. Angular stands for Almost Native Graphics Layer Engine. In short, it converts OpenGL APIs to hardware-level APIs supported by each OS. So, it translation from GLES2, 3, and 3.1 and 3.2 to Vulkan Desktop OpenGL and Direct3D 9 and 11, also Metal backends. Metal sounds a little bit strange. Metal is for Mac and iOS backends. As you know, DirectX is for Windows. In one sentence, we can say that Angular is a wrapper around OpenGL. So next, looking for Angular architecture. This figure is a simplified representation of Angular architecture. For better understanding, I will explain the core sequence of drawArray method, which is often used in Angular. This figure is the file where the drawArray method is defined. Entry point includes the validation and context part. In validation part, it verifies the arguments and types of each function. The context part calls the actual function and converts it for each OS backend. This figure is an entry point of drawArrays. If you look at this, if you look at this, you can see that there are validate and context call, right? If we pass the validate part, we reach this code. This code. In here, call to draw arrays implements for each actual backend. To implement the draw array for each backend, Angle implements the class method as virtual and inherits it from the backend. And inherits it from the backend implementation class. Next, let's check the M implementation class. Look at the code. Draw array is defined as a virtual. Inherit the context input class from each backend and make the actual draw array method. Also, we look at draw arrays in the Vulkan backend as an example. Just recheck. The context input class is inherited from Metal, Vulkan, GL, and Direct3D 9 and 11 to implement actual method. Also, the other methods are similarly implemented. As I say, let's check Vulkan draw array method. This code is the draw array in the Vulkan backend. Looking at the code, call the setup draw method and call the draw method. This code use the Vulkan backend as an example. So Metal and Direct3D are also implemented with the same structure as this. So next, let's check the order of calls from WebGL to Angle. WebGL to entry point of Angle. WebGL is a JavaScript API for rendering 2D and 3D graphics within any compatible web browser without the use of external plugins. WebGL uses Angle project as a backend to support the same level of rendering on multiple platforms. WebGL has two major versions, WebGL 1 and WebGL 2. Also, WebGL 2 includes WebGL 1. Additionally, the standards for WebGL are defined by Kronos Group. It is an architecture that includes WebGL. Angle architecture is the same, only add to the WebGL part. It is also based on WebKit browser. Chrome browser uses an interface named GRES interface in the command buffer system. They use that interface to call Angle entry point. However, we will explain based on the Safari browser. Now, let's look at the process of reaching the Angle entry point in WebGL. So, also we use draw arrays as an example. Before that, we check the idea where draw arrays is defined. Usually, methods that user can call in web browser are defined in IDEA files. In other words, if we look at IDEA, we can check the function that can be called. This is the implementation code of WebGL draw arrays. There is a couple of validation, and after that, the draw arrays of the M context object called. M context is a graphics context GL object and is defined in the header file. Next, we leave the graphics context GL object. So, looking at this class, draw array is a virtual method. So we need to find class that inherits this class and implements the draw array method. This graphic context GL angle class inherits graphics context GL class, and as you can see, define the drawArray method. The following are the drawArray defined in this class. Look at this code. Look at this code. The GL drawArray is being called, and as we saw at the beginning of the angle architecture, this method calls entry point of angle drawArrays. Okay, that's it. We learned about angle and WebGL architecture. Next, let's take a look at the one-day vulnerability in the angle project. So, I will describe the 4 bugs I found. There are more bugs, but for the sake of time, I describe the 4 bugs that I think are interesting, and we exploit transform feedback bugs in the exploration part of this talk. The first bug to analyze is the WebGL bug that I first reported. Also, POC is so simple, so there was no difficulty in the analysis. The root cause of this bug is that there is no validation of width, height, and depth when using the text storage read method. A prototype of text storage read is here. As you can see, all the other arguments are integer type except for target internal format. Text storage 3D specified all level of a 3-dimensional texture or 2-dimensional array texture. Also, the text storage read method is internally called to initialize for component data method. We covered the next slide. For your information, the texture is an object that contains one or more image that all have the same image. Also, the texture has a limited size. A heap-based buffer overflow occurs in the comment tree of this function. First, get test row with offset data pointer method in comment 1. When calling offset data pointer, y and z are used as a parameter. Y and z are loop counter for depth and height. This value is passed by user when calling text storage 3D. As you can see, the offset data pointer gets a memory space to be accessed as y and z based on data without any verification. Also, test row is used to get test pixel in comment 2. Again, there is no verification here. If the attacker passes a depth, height, and width that is larger than the current texture size, then out-of-bound read occurs when trying to access test pixel in the mem copy. So this is the POC code for the bug. It is so simple, right? This result gets after running POC with window debugger. To get this result, we need to attach the GPU process of the Chrome browser, not render process. Next, let's look at an interesting user-after-free bug. This is a bug that occurred in drawArray method, but that does not mean it is not problem in the drawArrays. DrawArrays did several verifications before drawing. When do this, there was a problem with the object being verified. The bug type is user-after-free. This is caused by not validating already delete texture object in the draw array verification process. Also, this bug pattern helps to find an exploitable vulnerability in Safari. This function is called internally when draw array is called. If you look at comment 1, use after free occurs when you use a texture that has already been removed. This function is one of the functions that draw arrays validate several states before drawing. Looking at the code commands, it is expected to be a function that validates whether a rendering feedback loop exists in the frame buffer before drawing. It seems weird to mention of texture object in the frame buffer validation function. But according to OpenGL standard, it is specified that the frame buffer object should be use a texture or render buffer object as the rendering target. This code is part of the POC code. As you can see, to trigger is so simple too. You just need to remove the bounded texture before calling draw arrays. If you want complete POC code, can be found by searching for the issue number or title on the crbob.com. This is the result getting with address integer. Next, we move on to Safari vulnerabilities. As we knew, Safari uses angle 2. So, when testing angle bug, we should test whether they can be triggered in Chrome, Safari, and Firefox. This bug can be triggered in Chrome and Safari browser. And the bug type is heap-based buffer overflow, caused by insufficient parameter validation of this method. Also, this method is a wrapper method that calls draw array multiple times. It is not the default WebGL method, so to use this function, we need to enable some extension. To enable the extension is shown in the POC part. This code is WebGL's MultiDrawArray WebGL method. Already we know this is not a part of Angle. It is WebGL part in the Safari browser. So the problem is this point. Not enough validation for draw count. Let's take a closer look at the validate offset method. In this code, to check draw count and offset are less than the size. It means the size variable should be greater than draw count and offset. But the problem is, if the sum of draw count and offset is greater than size, it is not checked. So it leads to a heap-based buffer overflow. This is part of POC code. First, to use MultiDrawArray, you must use the get extension method like this code. Next, we call MultiDrawArray WebGL. At this point, we passed draw count and offset bigger than the provide array size. So as a result, heap-based buffer overflow occurs. This is the result getting with address integer. And this bug can trigger the Chrome browser as the same POC. Next, we will deep digging into the exploitable WebGL bugs. This bug also occurs when validating several states in draw arrays in Angle. This bug occurs in the transform feedback feature. Also, transform feedback use a buffer object of angle to validate transform feedback before calling draw arrays. At this time, the already delete buffer is used. Before drawing, in DrawArray method to validate about transform feedback object, at this point, can use the already deleted buffer object in the transform feedback object. Transform feedback use a buffer object to store the output of the vertex shader. The stored value in the buffer object is used by GPU for faster drawing. Also, for your information, transform feedback is available start with WebGL 2. And among the three main browsers, Safari was the latest to support it since Safari 15. However, I never used WebGL for anything other than bug hunting, so I don't know the detail of how it works. Okay. The bug pattern is similar to the getSampler texture bug. In comment 1, the code finds the buffer object from the buffer handler array. However, the buffer handler may contain the removed buffer object, and as a result, the crash occurs in comment 2 when getCurrent buffer access the already deleted buffer object. Before analyzing in detail, look at the buffer and resource class. As you can see, buffer class inherits from resource class. And in the resource class, define a structure called mUsageReference. Here. This structure is important for our exploit. We will use this use-after-free bug to put the attacker's desired value into the mUsageReference field. Now, analyze where the crash point. If we remember correctly, the crash occurs in the setBufferForWrite method. If you look at the method code, it receives the buffer value and calls the setWriteDependence method. After that, the member method of resource class calls set used by command buffer with QSerial. At this point, the second argument is set to true. Next, let's look inside this method. Since the writing argument is true, it enters the if statement. So, a value is put in the member variable of the mUsageReference. As you can see, both variable type are boolean type. After that, put the value in the CMD buffer QSerial field. At this point, return value of the max method was always 6. I found this by debug. Still, I'm not sure exactly what this field does. This code is part of POC to trigger the bug. Initially, this is the base code of used transform feedback feature in WebGL 2. As you can see, before calling DrawArrays, just delete the buffer object. This deleted buffer object was bound to transform feedback target. here. So this is the result with address sanitizer. So far, a total of 4 bugs have been analyzed. This is the location of bugs in the WebGL architecture we look at today. I didn't have time to cover them all, but Angular is still one of my good attack vectors because it has to communicate with the GPU. GPU needs more permission than a renderer, and whenever the JS standard is updated, the WebGL feature is also updated. Also, WebGPU is to be officially released soon. This part will be a good attack vector. Next, I will discover the detail of how to exploit the bug we just looked at. So, finally we reached the more interesting part. In this part, I explain how to exploit the transform feedback bug that we looked at. Pause at all, let's recap to what we have. As you can see from this figure, we can control to a variable of M usage reference structure of already deleted buffer object. Now let's see how we can stably reallocate memory that has been deleted. To find a way to reallocate, we must know how the buffer object is allocated. As you can see, some buffer object created by the create buffer method. When called create buffer method, internally called create buffer of the context class. This method is also called the allocate new object method. At this point, allocates a buffer object using a new operator. Also, buffer manager class does not override the new operator, so it is allocated to the normal heap. For reallocation of the pre-buffer object, I use the buffer data method. When we call this method, as you can see, allocates an initialized memory with get0 field buffer. In the method, use malloc function. So for the list, we can easily allocate in the delete buffer object. So now look at the exploitation steps. I explained 5 steps, but before that, let's run the basic of JS object. Okay. Before heap spray step, explain to the butterfly of JS object used in JavaScript core. Check it with a simple JavaScript program. As you can see, this code simply defines 2 arrays and puts value of different type. After that, check the result of array and array2 with the dumpCell function. dumpCell function is JavaScript core native helper function. So now let's look at the result of array. Left side. The array type became array with double because it puts a value of double types. Here. Next, array2 type became array with contiguous because it puts a value of object type. Now, let's see what this code looks like in memory. This figure is a memory representing the two arrays created in the previous. The blue color is double type array, and the other is contiguous type array. First, looking at the double type butterfly, it points to a value of 1.1. And above this, you can see the value indicate to the length of this array. So, JS object has two types of lengths. It is called vector length and public length. The vector length is a writable size. Public length is a readable size. And when we use the length property of some array, get a public length value. Initially, when we do out of bound read and write, we need to modify the vector length. Next, looking at the contiguous type butterfly. It points to a value of some object. And above this, you can see the value indicate to the length of this array. You can see that it has the same structure as double type array. Now, let's start the real step 1. This code is the heap spray part in the exploit. The purpose of this is to spray the butterfly in memory as checked in step 0. At this point, the upper few bits of butterfly are fixed. These bits are fixed. Using this, we can predict to spread butterfly address. When step 1 is executed, many butterflies are created in memory. As you can see, the sprayed memory has the same shape as the one on the right. Keep this shape in the mind. It used until the end of this talk. Now talking about spray code. The value parameter is important. We should put the predicted butterfly address in the value parameter. The value must point to this memory. Looking at this line. Looking at this line, we add offset OX 5D to the value. If offset OX 5D is added to value, it points to the length. If offset OX 5D is added to value, it points to the vector length of another double type array. Like that. If the bug is triggered after this, the value becomes the M usage reference field of the freed of the delete buffer object. Next, this code is part of trigger function. After calling delete buffer, it attempts to reallocate by buffer data on the already freed memory location. The reallocated value is in this array. Before trigger the bug, put the value at index 55 of this array. 55, this array. After that, we trigger the bug. Index 55 is the location of M usage reference field I found by debug. As we know, when trigger the bug, we can reach this method. At this point, M usage reference should be replaced with exactly the value we want. The target we want to change is the vector ranks and index 0 of the double type array in the sprayed butterfly. Let's look at this a little more. This figure shows what the trigger function does. If the M usage reference field has been reallocated, it updates CMD buffer queue serial and CPU read sync and CPU read mem 30 field. As I mentioned, the vector ranks of double array and the index 0 are changed to those value. So the vector ranks was changed from 5 to OX65. Now this array can be out of bound read and write. Using this to proceed with next step. For now, we can call this array that has been resized by a bug a corrupted array. So look at this line. The index 8 of the corrupted array has the ranks field of another double type array. We change the ranks of this array to 1338. Change 1338. So now we have a fake array of the large size. Now we can do something with this fake array. One of them, for stable exploitation, we can get a valid structure ID of JS object. This code is getting a valid structure ID. It is a little bit complicated, but it is fun. It is easy to understand the code by following it line by line. Also, the red box is a double array and green box is a contiguous array. Looking at the first line, we put the fake structure ID into the index 0 of fake array. Then the memory changes like this. In next line, we put the index 5 value of fake array into the index 1 of fake array. After that, change the value of index 5 of fake array to value plus OXC0, so C0. This is the memory shape that was executed before the alert. In browser exploitation, alert is also good breakpoint. Of course, if you have done your exploit, should be remove the alert message. So, as you can see, the value of index 5 of fake array point to the index 0 of fake array. As I mentioned, the green box is contiguous array. We are currently replacing the index 0 of this contiguous array. So, when we access the index 0 in this contiguous array, it will recognize the red box as an object. Recognize this address as the structure ID of the fake object. Then, the address of temp array is recognized as a butterfly pointer. For this, what will happen if we read the index 0 of the contiguous array? The answer is the next slide. Looking at the next slide, read the index 0 value of contiguous array. At this time, the index 0 value is patched based on the changed butterfly. For now, as you can see, butterfly points to the temp array address. So, get structure ID stored in the actual temp array, like this. So, you can use this. We almost there. Finally, we only need to explain how to make the address of and fake object primitives. Let's look at the address of method. We need to focus on this red box. First, put the object whose address you want to find out into index 1 of contiguous array. And after that, it read using fake array. As you know, fake array is double type array. So then you can get an object address in double format. Now turn on the fake object code, similar to address of method, but a little bit different. First, we need to create a fake object in memory. After that, put the fake object address to the index 6 of fake array. Now, read the index 1 of contiguous array. The fake object pointed to by address is recognized as an object. At this time, fake object must have a valid structure ID, so that an error does not occur. The core of address of and fake object primitives store and load two arrays of different type from one shared butterfly. So that's it. I have posted what we have run so far on GitHub, this GitHub. And as a small solution for my English, I'm also posting a version of this slide with my script. Now I switch to public. Okay, finally, let's take a look at the demo. Can I? Oh. Okay, first, check the browser version. Here. Okay, check the browser version, and after that, try to exploit. But it will be failed. Because it occurs to wrong predicted butterfly address. And then exploit is keep running. Exploit restart the browser and restart browser exploitation, because I'm In fact, I prepared it for submission to Font 1, so I only need to be successful in 3 times. If the found array message is shown, our exploit is success. And then crash the render browser. So, but the exploit is not the full exploit chain. So I only change to value of resters. As you can see, 1337 can confirm. So that's it. Thanks for listening to this talk. If you have experienced any trouble due to my English, please complain on Twitter. Thanks.
Thank you. There are a couple of questions. What are some of the tools you use as part of your workflow for finding and debugging these vulnerabilities?
I use tools for purging or code auditing. I make on my browser and debugging just LLDB on macOS.
Have you published your fuzzer? Is it available for people to?
Yeah. I think public fuzzer is not good for me because the other person already found that many bugs. Yeah.
Okay, thanks. Anybody answered? Anybody asked this question? Anonymous? All right. Are you able to share any limitations with Angle?
Limitation? Any limitation? Sorry. Angle is just a wrapper OpenJS. So the means limitation. I don't know what is limitation means.
Any drawbacks, weakness?
Weakness? Yeah.
Not good.
But Angle is just I mentioned, just OpenJS wrapper functions. And they are some validation part and is only some developer make validation routine, and then that part maybe will be corrupted, some mistake, that part. So if my answer is not your correctly answer, can I calm down and answer you? Calm down?
Yeah, sure. Whoever asked that, I guess it might be easier. Or if you want to explain now. Okay.
Okay.
Maybe they'll find you later.
Okay.
All right. Thank you. Can we give him a round of applause again, please?